Have you ever just stopped and wondered how a rocket can land itself on a tiny little platform in the middle of the ocean? Or how a robot in a factory can do its job with like superhuman speed and precision? Well, I promise you, it's not magic. It's the absolutely incredible science of modern control theory. And we're going to demystify how it all works.
So here's the big question we're tackling. How do engineers get these super complex systems to do exactly what they want? I mean, they're fighting against gravity, friction, wind, you name it. How do they achieve this seemingly impossible level of control?
You know, the classic image that comes to mind is that rocket. It's this massive, inherently unstable thing just balancing perfectly on a column of fire. It feels like it shouldn't work, but it's actually a solved problem in control engineering. Or let's take a look at a challenge straight out of a textbook, the inverted pendulum. Think about balancing a pencil on your fingertip. Now imagine a machine doing that, just perfectly and forever. This right here, this is the core challenge we're about to unpack. Okay, so to solve problems like that rocket and that pendulum, we first have to really define what we're up against. Engineers call it the control problem, and cracking it, well, that's where things get really powerful. To put it as simply as possible, the control problem is this. How do we take literally any system, whether it's a chemical process, a drone, or a robot arm, and force it to follow our commands down to the letter? The goal here is total, predictable control. So how in the world do we actually do that? Well, the first huge breakthrough was a technique called pole placement, and this was a revolutionary leap that pretty much changed everything. And the difference this made was just massive. See, conventional design was kind of like having only bass and treble knobs on an old stereo. You could only really adjust the most dominant behaviors. But pole placement? That's like giving an engineer a full studio mixing board, letting them precisely tune every single behavior of a system that's constantly feeding information back to itself, what we call a closed-loop system. So what are these poles we're placing? Well, you can think of them as the system's DNA. They define its core personality. Is it fast? Is it sluggish? Does it overshoot its target? Or is it prone to shaking? By moving these poles around, we can literally change the fundamental personality of the system. And how do we move them? We use this right here, the state feedback gain matrix, or as everyone just calls it, K. This matrix, this is the secret recipe. It is a carefully calculated set of numbers that tells the system exactly how to react to its own state to force its poles to go exactly where we want them to be. But of course, there's a catch. There's always a catch, right? For any of this to work, there's one fundamental requirement. The system has to be what we call completely state controllable. And all that really means is that our controller's inputs have to have a way to influence every single part of the system. If there's some part of it that we can't talk to, well, then we can't control it. Simple as that. So pole placement seems like the perfect solution, the end of the story. But engineers pretty quickly ran into a really big, practical, real-world problem, a blind spot. The whole idea of state feedback relies on the assumption that we can measure all the important variables of the system all the time. But what happens when you can't? What if some of the most critical variables are completely hidden from view? And trust me, this happens all the time. Just think about it. How do you measure the temperature burning away inside a jet engine? You can't just stick a thermometer in there. Or maybe the perfect sensor exists, but it's way too expensive or it's just not reliable enough. We have to have a way to control the system using only the information we can actually get our hands on. And that leads us to the next brilliant piece of this puzzle, the state observer. It is such an elegant solution to this problem of not having all the information. So what is a state observer? Well, it's basically a digital twin of the real system that's running in software. I also like to think of it as a state detective. Its entire job is to use the clues it can see to figure out the state of the things it can't. So here's how it works. It's a two-step process. First, the observer runs a perfect software simulation of the physical system, what engineers call the plant, and it uses the exact same control commands that the real system is getting. It's essentially creating a little virtual reality version of the machine. But here is the really clever part. The observer is constantly comparing its own simulated measurements to the actual measurements coming from the real world. Any difference between them, the error, is used as a correction signal. It nudges the observer's internal state, making its estimate of those hidden variables more and more accurate with every passing millisecond.
Now, for this to actually work, there's a golden rule. The observer's own internal dynamics, its own poles, have to be at least 2 to 5 times faster than the controller's poles. Why? It's like a scout that has to run way ahead of the army to report back on the terrain. The estimate has to figure out the truth before the controller needs to use that information to make a decision.
So now we can see the whole modern control loop in action. You've got the plant, the real system, with a hidden state. The observer builds a really good estimate of that hidden state. Then, the controller uses that estimate, not the real thing, to calculate the right action. And finally, the actuator applies that action to the plant. It's this beautiful self-correcting loop.
All right, let's put these two massive ideas together, pole placement and state observers, and see the complete picture of how modern control actually works.
You know, as one of the most famous textbooks in this field says, engineering is always about trade-offs. If you place your poles to make a system react super fast, you might also make it really sensitive to noise and disturbances. If you make it super robust, it might get a bit sluggish. There's no single perfect answer for everything. So how do you find the best compromise? This is where the whole thing evolves from an art into a true science. Instead of just picking pole locations by hand, modern methods let engineers define something called a cost function. You basically tell the math how much you hate error versus how much you hate spending energy. Then an algorithm calculates the one optimal gain matrix K that finds the perfect balance between those two things you care about. And this combination, this elegant dance of precise design, clever observers, and mathematical optimization, this is the brainpower running the world around us. It's inside the robots on an assembly line, it's in the autopilot of an aircraft, and yeah, it's in those rockets that land themselves back here from space. This technology gives us just a profound ability to command the physical world with incredible precision. And it leaves us with one last, really important question. Now that we have this amazing power to control complexity, what are the most important challenges we should go out and solve next?